Good afternoon. My name is Gustavo Araújo. I am Lieutenant Colonel of the Brazilian Air Force. This work I will present today, an architecture to process synthetic aperture radar signal on chip, was developed by me during my master's degree in 2015 and 2016 with the support of two professors from the Aeronautics Institute of Technology, ITA, Roberto Damori, who was my advisor, and Davi Fernandes. Since 1950, when it was founded by the Brazilian Air Force, ITA forms engineers and produces research in the aerospace area. It's important to emphasize that this work is not a project of a product for the Brazilian Air Force, but rather a work within a research line. I'm going to start this presentation with a quick introduction on synthetic aperture radars. Next, I will detail the scope of the work, that is, I will point out which modules of a SAR system were covered by the proposed architecture and its delimitations. Following, I will present the characteristics of the Field Programmable Gate Arrays, FPGA, which was the technology used in the architectural development. Then I will give a deeper explanation from a technical point of view of how the SAR processing algorithm was implemented in the FPGA. Finally, some results and analysis will be presented. A SAR system, roughly speaking, is a radar system that aims to produce images of the terrain. The major advantages of a SAR system compared to optical systems are its ability to produce images at night, through clouds, or even through treetops. There are several modes of SAR operation, regardless of whether these sensors are on aircraft or satellites. Here I highlight the three most common terrain imaging modes: strip map, scan, and spotlight. The strip map mode keeps the antenna always fixed and pointed in a lateral direction, right or left, producing an image, limited in width and unlimited in length. The scan and spotlight modes differ from the strip map mode because in these modes the antenna moves in relation to the platform to cover larger or smaller area at the expense of worse or better resolution. In the scope of this work, we restrict the implementation of strip map mode only. The two axes of the Cartesian plane that defines the area scanned by a SAR system are commonly called range and azimuth axes, the same as y and x axis, where the range axis means the limited width while the azimuth axis means the unlimited length. In this animation, the acquisition and storage of a raw data collected in strip map mode is exemplified. Keeping a route parallel to the azimuth axis, the radar transmitted modulated pulses, chirp pulses, and based on the reception time window and the modulation frequency of the chip signal, the received echoes are then demodulated, and after the analog digital conversion, they are stored in vectors where each index is related to the range of the sample. At each pulse repetition interval, the platform moves a short distance in azimuth direction. Then, a new pulse is transmitted and a new raw data vector is obtained and stored in memory. At the end of a predefined number of pulses, a raw data matrix is obtained, where each cell is related to a range position and an azimuth position. In this image, we observe the raw data obtained and stored by the Earth-1 satellite. As you can see, the image looks completely blurred. This is a characteristic of the raw data of a SAR system. The targets are, in a sense, hidden in this image. If you want a useful image for analysis, it's necessary to apply a processing algorithm to the raw data in order to obtain the focused image. This image below is what we get after processing the raw data above. A generic SAR system comprises an RF subsystem responsible for generating, transmitting, and receiving pulses, and delivering the raw data to a processing subsystem. After processing, the image can be transmitted or not to a remote station. Finally, the images are presented through a display subsystem. The scope of this work is restricted to the processing subsystem only. In order to emulate the RF subsystem, previously obtained raw data were used, which were stored in memory cards. To emulate the display subsystem, an application with LabVIEW software was specially developed on a PC. Thus, the proposed SAR processing architecture reads the raw data samples on a memory card and, as the data is processed, sends the processed image to the PC via a serial peripheral interface SPI connection. The development of the architecture started from some requirements that we defined previously. Our goal was to design a low-cost architecture that could be applied to small platforms such as UAVs or mini-satellites. To accomplish that, the system should have the following properties: power efficiency, reduced dimensions, and lightweight. Real-time application was only a desirable requirement, but we were aware that if we couldn't meet the processing time necessary for a real-time application, the next steps would be to find solutions to speed up the processing. Field Programmable Gate Arrays, or FPGAs, was the technology used to implement the architecture. An FPGA is a chip without a specific application. Roughly speaking, an FPGA is a huge array of logic elements that, at each system initialization, are electrically interconnected to perform a specific function. This example illustrates how simple logic gates can be synthesized in an FPGA by means of a hardware description language such as VHDL. In the same way, it's possible to synthesize simultaneously in the same FPGA a great variety of hardware of high complexity as well as microprocessors. Here we have some FPGA features. Flexibility is a key feature of FPGA, since it can be easily reconfigured. They integrate easily with any design because its functionalities can be easily changed. Since they do not require a manufacturing process after the design process, they are quickly made available to the market. And they are power efficiency, reduced in size, lightweight, and low cost. In the figure, we see a comparative chart of cost and power versus performance. In it, different models of 3 FPGA manufacturers are presented. Considering the low cost and power efficiency of the Cyclone FPGA manufactured by Intel FPGA, we have chosen it to be used in our architecture. Another reason to have chosen it was the fact that we already have Cyclone 4 FPGA development boards available in our lab. This is the D2 115 FPGA development board manufactured by Thoracic, which contains, in addition to an FPGA Cyclone 4, a larger number of components to support the design of a hardware. The board has memory, switches, LEDs, input and output interfaces. The Cyclone 4 FPGA, on the market since 2009, was built with 60 nanometers technology, and the cost of this board is only $595. There are several algorithms capable of focusing the SAR image. We chose to implement one of the most consecrated algorithms, the range doubler algorithm. It has an advantage to allow two-dimensional data to be processed separately in range and in azimuth. In the range processing, each column of raw data is submitted to a Fourier transform. Then, the post-compression in range is performed, multiplying the data sampled by the match filter or transfer function. This operation in frequency domain is equivalent to the circular convolution in time domain. After post-compression, the data column is subject to an inverse Fourier transform, returning to the time domain. This procedure repeats until all columns in a predefined block of data are processed. In azimuth processing, data already processed in range is sent to the FFT in rows. Then, the range cell migration is corrected by moving the cells in the range direction, and next, azimuth pulse compression is performed. Finally, the inverse FFT of each of the lines is executed, resulting in the processed SAR image. To implement an algorithm that handles a large amount of data, we had to use the 128 megabytes SDRAM available on the development board in a very optimized way. The implemented logic required at least 3 memory areas, each having the size of a raw data block, one for the azimuth transfer function, one for the buffer containing the data being processed, and one for the buffer which stores the already processed data, the image to be displayed. Thus, we defined the complex variable as float point, 32-bit real plus 32-bit imaginary, and the data block dimension as 2048 by 2048 pixels. Therefore, each block has a total of 32 megabytes. That way, there are 32 megabytes left in memory to be used by the other variables and system code. A negative consequence of frequency domain processing is that the circular convolution produces some discontinuities at the edges of the image. The correction was made possible by the overlap and save methods. To do this, for each processed data block, a calculated number of columns are thrown away at the beginning and at the end of the block. In addition, final columns of a block already processed in range are reused in azimuth processing of the next block. As an undesired consequence, the processing speed is decreased, since fewer new samples are used in processing of each block. This figure represents the final design of the architecture. On this purple rectangle are all the components that were synthesized in the FPGA. There are buses, represented in red or orange, intellectual properties, IP, in light blue, or especially customized hardware components, dark blue. Hardware external to the FPGA present in the development board are represented in green. In the next slides, I will detail some of the main components. NEOS2 software processor is an IP provided by Intel FPGA, as well as the other IPs used in the design. It is a microprocessor defined by a hardware description code synthesized in the FPGA. NEOS2 controls algorithm flow, interfaces with all these external components through IP controllers, also synthesized in the via FPGA, generates the range transfer function, uploads raw data from SD card to SDRAM, and sends the processed data from SDRAM to SPI. The set of IPs, Fast Fourier Transform, FFT, and Direct Memory Access, DMA, were also synthesized in the FPGA to play an important role in the processing algorithm. This set performs the discrete Fourier transform, 32 bits float point format, supports data formatting with specially designed circuitry, implements the range cell migration correction, executes matrix transposition, and carries out the overlapping save method. The post-compression hardware is a custom hardware specially designed in VHDL. The post-compression hardware accesses SDRAM through Avalon memory mapped interface for reading and writing, generates azimuth transfer function with assistance of float point IPs, and performs complex multiplications and additions for post-compressions. To analyze the quality of the processed image, we use the point-target impulse response method, both in range and in azimuth. To do this analysis, we used a raw data generator system to create a file with data equivalent to the SAN containing 3 point targets. The raw data were processed, generating an output file. The 3 points representing near range, medium range, and far range were analyzed using MATLAB. If we zoom in on one of the targets, we can draw graphs like that. The center of the graph represents the response to the exact position of the target on one of the axes. However, as it moves away from the target center, we note that unwanted portions of the reflected energy are still present. 3 parameters were used to verify the quality. Impulse response width, that measures the width of the main lobe at the -3 dB position. Peak side lobe ratio, that measures the ratio between the peak of the main lobe and that of the secondary lobe. And integrated side lobe ratio, that measures the ratio of the amount of energy contained in the main lobe to the amount contained in the secondary lobes. Our results were in accordance with recognized standards. Still with the objective of evaluating the image quality, raw data from satellite SAR systems were also processed. For this, we have developed an IDL preprocessor to extract parameters and raw data from different public domain files. We used data from the ERS-1, ERS-2, and ALOS-1 pulsar system. On the left, we have a non-georeferenced image resulting from ERS-1 data processing in the region near Mount Fuji in Japan. On the right, we have an image available in the Apple Maps app just to illustrate the region, of course without any objective of comparison, since this is an optical image. They are different things. It should be noted that the images did not undergo by any kind of post-processing to reduce speckle noise. In this image, we have the result of S2 data processing. This is the port and the city of Rotterdam in the Netherlands. And here we have the result of processing of ALOS 1 pulsar data on the Guanabara Bay in Rio de Janeiro. This process was performed with data from the S1 sensor on the Andes Mountain. 3 blocks were processed and placed side by side without the use of the overlap and save method. Note that some noise at the junctions of the blocks can be easily identified. However, in this processing of the same raw data from the previous slide, the overlap and save method was used to correct the unwanted effect at the edges caused by the circular convolutions. Note the absence of faults in the junctions of the blocks. And finally, this image is the result of the continuous processing of 17 blocks with the overlap and save method. Although real-time processing was only a desirable requirement, we also analyzed the possibility of applying this architecture for real-time processing. In this case, it is crucial that the processing time of a block does not exceed the time required to acquire all the samples of a block, because if this happens, there will be a buffer overflow. Taking the parameters of the S1 sensor as an example, we calculated the time required to acquire all samples of a block, 0.882 seconds. But using a 50 MHz clock, our system took about 20 seconds to process an entire block. At first glance, the result may seem somewhat disappointing. However, it is a fact that some improvement can significantly reduce processing time. For example, we can replace the 50 MHz clock for a faster clock. Since the technology of the hardware used is already 10 years behind, another solution would be replacement of the FPGA for a more modern and faster one. It is also possible to replace the Neo 2 soft processor with a hard processor that supports a faster clock. There are several low-cost FPGAs that comes with a hard processor. We could also instantiate more than one processing unit, so that we could process multiple samples at the same time in parallel. Another solution that would significantly speed up processing would be to handle variables like fixed points instead of floating points. This would not only reduce the amount of traffic bits, but would also imply faster math operations. Further information regarding this work is detailed in a paper we published in last September in IEEE Aerospace and Electronic Systems magazine, entitled Cost-Sensitive FPGA Implementation of SAR Range Doppler Algorithm. The paper can be accessed through this link, and if anyone wants to contact me, here are my email and phone number. Thank you very much.